Alright, so this here is power series. We were tasked with finding the radius and interval convergence. We're going to test the endpoints once we reach it. So to start, we're going to perform some algebraic manipulation. We're going to factor out a negative 1 to the n. Alright. So from there, we're going to perform the ratio test, which states that as the limit of n to infinity of a sub n plus 1 over a sub n, if its absolute value of r is less than 1, it's convergent, and absolute value of r is greater than 1, it's divergent. So, performing that, all we did here was add an n plus 1 everywhere there was an n in the original series. And then we're going to multiply by the reciprocal, which will be n over, or n rather. It will be n square root of ln of n over the top, which will be minus 1 to the n to the nx plus 3 to the n. Now we can start canceling. So we'll have a minus 1 to the n times a minus 1 to the first, just breaking this apart. And a 2 to the n times a 2 to the first, breaking that apart. And doing the same with the x plus 3. Copy the bottom. So from there, we can now start canceling. Minus 1 to the n will cancel with that minus 1 to the n. 2 to the n will cancel with that. X plus 3 to the n will cancel with that. So we're left with, we'll carry our limit down. We're left with a minus 1, a 2, and x plus 3 over, we'll keep the n square root of ln of n over n plus 1 over n plus 1, or over natural log, square root of natural log ln of n plus 1. Then we have to figure out where this goes to. So we have this down here. We have the limit as n goes to infinity of n square root of ln of n over n plus 1 square root of ln of n plus 1. We're going to break this apart into two limits. Times we did was break apart the two limits for like terms. Now, we know that the limit of this by leading powers on the ends will go to 1. So this will have a value of 1. But here we have to perform some manipulation. So we'll factor out the square root to the whole thing and bring the limit inside. So we have that. And then from here we'll perform L'Hopital's rule. And that will say take the derivative of the top, be 1 over n over derivative of the bottom, be 1 over n plus 1. So then it will be limit as n goes to infinity. Bring that to the top, bring that down will be n plus 1 over n, which we already defined that limit as n goes to infinity of n plus 1 over n goes to 1. So that equals square root of 1, which will equal just 1. So we'll end up with a 1 times 1, which just equals 1. So we know that this whole thing goes to 1. So we can now say we've taken a limit, so we just have the absolute value of minus 1 times 2 times x plus 3. And we have to force convergence to be able to find our radius of convergence. So we'll say it's less than 1 because we just stated that r had to be less than 1 for it to be convergent. So we know that this minus 1 will go away because we're taking the absolute value. So we're just left with 2 times x plus 3, carrying the absolute value down. It's less than 1. We'll divide the 2 over. We'll get x plus 3, absolute value, is less than 1/2. And that will be our radius of convergence. Because the form for radius of convergence is x minus a is less than 1. This being a radius of convergence. So this is the form we wanted in. We can then say from there that the possible endpoints for convergence will be -7/2 and -5/2. So this is what we'll be working with. It's coming back up here. We'll try x equals -7/2 first. We'll plug that back into our original series that we simplified. So, -1 to the n, 2 to the n, just copying from here. We'll plug in our -7/2 where the x is. And then we'll simplify from there. That will be series from 3 to infinity, -1 to the n, then -7/2 plus 3 will be -1/2. So we'll have -1/2 to the n over n square root of ln of n. That'll equal -1 to the n, 2 to the n another minus 1 to the n, and we carry this n through to both of these, both numerator and denominator. The 2 to the n will follow the bottom. Those will cancel. We'll be left with actually we'll be left with 2 minus 1 at the end will give us just 1 on top. That'll be over n square root of ln of n. From there, we can now test this point for convergence. So we will do the integral test. So we'll say from our bounds from 3 to infinity of 1 over n square root of ln of n dn. We'll form u sub taking the derivative of u, be 1 over n dn. And we're going to leave our bounds the same because we're going to end up plugging u back in. So we'll copy our bounds. 1 over n dn will plug straight in as our du. We'll be left with 1 over square root of u, plugging u in for ln of n. Bring that to the top. And aggregate from there. So we just performed some simplification along the way. Brought this up, plugged u back in, brought it back to the square root. Factoring the 2 out, it will be square root of ln of infinity minus square root of ln of 3, which goes to infinity, which is not a finite number, so therefore we can say that we can say that the integral diverges by integral tests. Therefore giving us our first point. It's just a parenthesis. So now, erase this. And we're now going to test our second point, which will be negative pi over 2. So when x equals negative pi over 2, we'll start by plugging this back into the original series. N equals 3 to infinity. Minus 1 to the n, 2 to the n. Negative 5 over 2 plus 3 to the n over n square root natural log n. Simplifying that gives us negative 5 over 2 plus 3 will be 1 over 2 to the n. And simplifying this, distributing the n through carries the 2 to n. 2 n will follow the bottom, 1 to stay on top, times an n square root natural log of n. 2n will cancel. We'll be left with series as n equals 3 to infinity of minus 1 to the n over n square root natural log of n. You can tell this is alternating series, so we use alternating series test. With our a sub n defined as absolute value of this, so it'll be 1 over n square root natural log of n. So we know that a sub n is positive. We know that limit as n goes to infinity of 1 over n squared natural log of n will equal 0 because this is being dominated. The function is being dominated by the denominator. And then we know that 1 over n plus 1 square root of natural log of n plus 1 is less than n. So we know that the a sub n is decreasing because this is being divided by a bigger denominator, so the number is smaller. So every successive term will be smaller, so a sub n is decreasing. So therefore, by the alternating series test, we know that the series as n equals 3 to infinity of minus 1 to the n, n square root of natural log of n converges. So therefore, we can say our second point, which will be where we got all this. Convergent, shown by the bracket, and divergent. That is the final answer. Thank you.